We'll continue with tutorial 8, question 627b. In these questions, we have a vector x of 0 that belongs to R3, and we are saying that the entries of x0 are non-negative entries. So we basically have some entries here and some entries here, and then they are all real numbers and they are non-negative numbers, and the sum of these three entries equals to 1. Now, we are then asked to basically construct x0 from c1v1 plus c2v2 plus c3v3. And remember that v1, v2, v3 are the eigenbases, and we can check these are the three eigenbases, and we can check that they are independent. How do you check that they are independent? You can form P1, P2, and P3, and then you can perform Gaussian elimination, and you'll have three pivots showing that these three columns are independent. That's one way to check. The second way to check is that we have three different eigenvalues, and because we have three different eigenvalues, the theorem in theorem 2, page 272 of Lay 5th edition, if you read that, then it says that the eigenvalues that are distinct will generate distinct set of eigenvectors. So here I pull out theorem 2 from page 272. Let's read together. It says that if v1 to vr are eigenvectors corresponding to distinct eigenvalues, so lambda 1, lambda 2 are different values, then the set v1, v2 up to vr are linearly independent. So what it means is that if we have distinct eigenvalues, it will generate independent eigenvectors. Okay, they will not be dependent. You can see the proof here. So there are two ways to show that in our problem P1, P2, P3 are independent. One is to apply this theorem and says that since the three eigenvalues are different, then v1, v2, v3 forms an independent set. The other one is by brute force. We generate the eigenvectors and we put this as a matrix, and we then reduce it, and then we can, of course, here will be v1, here's v2, and here's v3, and then we can check that there are three pivots to show that they are independent. Now, since they are independent, therefore the entries c1, c2, c3 are independent. So what we are basically saying is that x0 can be formed by v1, v2, and v3, and place it as a column vector, and then we have c1, c2, and c3, and basically if you think of this as the P matrix, then basically we multiply the P inverse on the left hand side, then we will have c1, c2, c3 on the right hand side. This will reduce to the identity, and on the left will be P minus 1 x0. So basically this is a 3 by 3 matrix multiplied by x0, which is a 3 by 1. We'll get the 3 by 1, and this will be unique. Now, the second fact given to us is that we are going to use W, which is a vector with 3 ones, and then we are going to say that W transpose x0 therefore is equals to W transpose c1 v1 plus c2 v2 plus c3 v3. Now we can open this up to say Wt c1 v1 plus WT C2 V2 plus WT C3 V3. Remember that C's are scalars. So this is equivalent to C1 W transpose V1 plus C2 W transpose V2 plus C3 W transpose V3. Now study carefully the entries of V2 and V3. So let's see what is V2 and V3. V2 is equals to, these are the entries of V2 and V3. Since W transpose V2, what does that mean? W is 1, 1, 1. The entries of V2 is 1 minus 3, 2. So therefore, this equals to 0. Similarly, W transpose V3 is equals to 1, 1, 1 multiplying by minus 1, 0, 1. And this also is equals to 0. It implies that these two entries here are equals to 0, leaving us as W transpose X0 is equals to C1 W transpose V1. Therefore, we can conclude that C1 is equals to 1. Since there is no contribution from V2 or V3 at all in this equation, right? So let's see this in the last part of Q627b, I forgot to mention that I know that this is the correct answer, C1 equals to 1, because we are given that X0, the entries are non-negative, and it sums to 1. And what you see is that in V1, the entries of V1 is equals to 0.3, 0.6, and 0.1. So the entries of V1 is also summing to 1. So W transpose V1 is equals to 1. And hence, we know that C1 equals to 1. That's the proof. Thank you.